I'm going to talk about quantum phases of matter today. And first, I'll try to give you some motivation from physics, and then I'll try to formulate some mathematical problems which are not solved, and possibly a solution would be interesting. And then I'll show you some preliminary results that some progress that people were able to make in the last few years. So the question is, the question is basically to like one of the basic questions in physics, how to describe phases of some systems. And we usually have some space of parameters, and we have some loci where we have phase transitions, so some properties drastically change, and we have the complement of this, which is like space of good phases. And what we are usually interested in is homotopy type of this space of phases, what are the connected components, so what are phases itself, and possibly some high homotopy groups, like loops or surfaces which describe some topological defects in this for the systems. Well, one setup where we can try to make this problem precise is a setup of gapped phases of matter. And by that, I mean the following. We have some quantum many-body system at 0 temperature, and it has some Hamiltonian such that interaction between degrees of freedom which are far away decays rapidly. And this Hamiltonian has a spectrum like on this picture. So we have a unique ground state, and we have some excited states of this Hamiltonian, which is separated from this ground state by some finite energy, which is strictly greater than 0. And we want to classify such systems up to deformations of the Hamiltonians, which preserve this gap. And in the last few decades, people have discovered a lot of interesting states which are not trivial, starting from the discovery of integral quantum Hall effect and others, like fractional quantum Hall effect, topological insulators. But of course, like to describe system like real system, in the real world, we really have particles which with some Coulomb interaction, and it's very hard to prove something about this. So we built some model, and we'll be assuming that we have some lattice in their Euclidean space and with some Hamiltonian, and in case we have some symmetry, we may consider like a G-equivariant version of the problem, like consider only deformations which preserve this Hamiltonian. But I'll formulate everything more precisely.
Excuse me, what is the meaning of IQHE or FQHE?
Yeah, this is integer quantum Hall effect and fractional quantum Hall effect.
Okay.
I will describe the difference between them.
So Nikita, we have a question in the chat. Ask you about, isn't the t equals 0 non-physical?
Right. So of course, in real world, we usually have systems at non-zero temperature. But the thing is, if we like also include this temperature, some phases can be connected in the space of like states finite temperature, but they may not be connected strictly at 0 temperature. And we can really see like many manifestation of the fact that the states at 0 temperature in different phases at very low temperatures. But yeah, strictly speaking, yeah, this is a bit unphysical that we consider like it's strictly at 0 temperature. But it is important. Well, it is important to do that to make the problem mathematically defined. Well, the problem that we actually going to solve is not about Hamiltonians, because if we consider, well, if we have some Hamiltonians which have the same ground state, we can consider just some linear combination of such Hamiltonians, and this linear combination has the same ground state, and it is also gapped. And it is not difficult to argue that this space of Hamiltonian with the same ground state is contractible. So we have some sort of fibration of the space of states with the base of space of states and with contractible fibers. And what we really want is to classify the space of ground states, possible ground states, and equivalence that we define in the states, if our Hamiltonian has some nice locality properties, is that the states can be somehow adiabatically connected by a different Hamiltonian, which, well, if the original Hamiltonian is local enough, this new evolution Hamiltonian should also have some good locality properties. Also, we should include certain stabilization of the system. So we should allow to add some degrees of freedom which are completely decoupled. So the states on them looks like just tensor product of some pure states. And the reason why we want to do that is because we want all systems which are just decoupled spins to be in the same phase, because it seems physically natural. So, and schematically, what we're trying to do is like try to classify states which are connected with each other by this some evolution by some local Hamiltonians, which we can, well, in physics, people usually approximate this evolution by this kind of pictures where each block corresponds to some unitary operator. So it's just an exponent of some local Hamiltonian. But that's, of course, just approximation and just schematic picture. But it's sort of a slogan that we want to like extract all the information about the phase just from the states, just from entanglement patterns of the state. You can find, for example, in a nice book by Xiaogan Wang and collaborators. But this space of states is very difficult in general, and we want to well, consider just some class of the states, which we can introduce by noting that there is some natural operation on these phases. That is, they can be stacked. We can just consider composition of two systems, and we have some tensor product state in these systems, and we can consider again equivalence under this evolution by local Hamiltonians. And this operation is associative, commutative, and has a neutral element, which is this trivial phase of decoupled spins. But it is not a group because not elements are actually invertible. And there is a special class of states, which we call invertible, and it was introduced by Kitaev, which is kind of resembles, well, it has motivation from K-theory, which is applicable to free systems, but will be interesting in interacting systems. And so these are states which such that there is some inverse for them, so that we can take another state, compose them, and the resulting state can be transformed into trivial phase. And that excludes other states which are non-invertible, which are, of course, more interesting. And they describe like systems like fractional quantum Hall effects and systems which have topological order. But it's very hard to describe them. So they're too complex, and we will be just considering this invertible in this talk. And we can hope to classify all such states in any dimension. For topological order systems, it seems like hopeless. So we can, well, this most we can hope for is to just find some mathematical object to describe them. But well, there are some idea that what kind of mathematical object we need for in 2 dimensions, but no idea in higher dimensions. But for invertible systems, it's much better. And in fact, for free fermionic systems, which are all invertible, we actually know how to do that. So there are some progress done in this. But first, let me describe like some additional structure in this invertible states that was conjectured by Kitaev. It's a nice structure that we expect that such phases, well, their space of such states, it forms a loop spectrum, that their space of such states in n dimensions, it is homotopy equivalent to space of loops in the space of states in high dimensions. And it has very simple intuitive explanation. If we have some loop in the space of, let's say, 3-dimensional systems, we can consider some interpolation so that we can fix some point in the space and consider like the states far away on the left and far away on the right, and consider some domain wall between these two half spaces. That gives one map, and the inverse map is constructed by the following. So it's kind of Allenberg Swindle trick. So we first well, we consider, for example, three-dimensional space, and like on this picture, we first create pairs of states and anti-state in one order, and then annihilate them in a different order. And that corresponds to some loop in the space of three-dimensional states. But it is constructed using some state in low dimension, well, in codimension 1. And there is actually conjecture for this loop spectrum, how it should look like, by Fried and Hopkins, that it should be described by some unitary topological quantum field series, in which are, well, in this work, they were characterized. And we can hope to try to prove this conjecture for lattice systems. And as I said, for free systems, we more or less understand what's going on. So like this free systems, they're classified by K-theory of some C-star algebra. But the interacting kinks we don't know. Well, hopefully there is some interesting mathematical theory that describes it. So we just want to find the theory, but we want to build some formulas that allow us to prove some results about these phases. So what we want from these formulas? First of all, we should somehow be able to work with these Hamiltonians, which are not strictly local. So the same kind of fuzzy version of these block pictures. Since we're talking about phases, they're actually defined in the infinite volume. So we want to work with the infinite volume systems. And also we want to somehow include stabilization and locality into this picture, which is not always obvious how to do, because like, well, it's easy to consider just some fixed algebra and like deal with it. But here it's important to like add additional degrees of freedom. Okay, and next I'll describe some formalism. Well, which is basically just application of method of quantum statistical mechanics. So yeah, now I'll try to be more precise. So what we mean by our system is that we have some lattice, which is a Delaunay set, so that it is uniformly filling our space and we don't have any accumulation points. And we'll be assuming that at each side we have some finite dimensional Hilbert space. We can consider either uniformly bounded, but some uniformly bounded dimensions of this Hilbert space. But some of the results are also applicable when dimensions of the spaces don't grow too fast. We consider like, well, we have natural algebra on this system. So we have algebra of on-site observables just in the morphism of this Hilbert space. And for any finite subset, we can consider tensor product of such algebras and consider co-limit of all such algebras, which is algebra of local observables. So they have some finite support in this algebra. And usually people then define like algebra of quasi-local observables, which is C-star algebra, and it's just norm completion of this algebra, and consider states on this system. But this algebra actually knows not too much about like about their system, so about the lattice. So it only knows like which sets of the lattice are local. And more appropriate algebra for us will be algebra of what we call almost local observables, which is certain subalgebra, which is not C-star algebra. And these are observables which can be well approximated by finite observables with accuracies that decays faster than any power. So more formally, we mean that we can define infimum. So we have some site J, and we consider like infimum of the difference of between, well, this observable and some observable localized on the ball at this side of radius r, and consider best possible approximation. So we can define the set of semi-norms for each natural number alpha, and consider completion of the space of local algebra with respect to the semi-norms, well, including the norm that natural norm in this algebra. And this algebra forms Friche space, so it's Friche star algebra. And I'll explain more why we actually want this algebra, why it's better. But first, let me proceed with defining other objects. Yeah, I just want to mention that there is a operation that we'll be using a lot in the following is truncation of the observable. So if you have some region A, we can consider averaging of the observable over all unitaries which act by conjugation in the complement of this region A. And that's kind of extracts from element of the algebra only the part which is supported strictly on this region A, so that it commutes with all elements localized in the complement of A. And having this algebra, we can define what we mean by Hamiltonians, by nice Hamiltonians. So of course,
I have one question: is this algebra looks a little bit like half of the Schwarz space? I mean, when you define it, so is it stable under holomorphic calculus?
Oh, I don't know. You mean? Could you explain a bit more what you mean by that?
Well, what I mean by that, for instance, when an algebra is in a C-star algebra, is stable which is not in the spectrum of an operator of an element, then the resolvent is still in the algebra. That's the main condition. So it's, if you want stable under resolvents, I mean, or under, yeah.
I don't know, but yeah, let's discuss it at the end.
Sure. But that's a very important property for K-theory purposes.
Okay, okay. Okay, let me proceed with the definition of Hamiltonians. So by Hamilton, of course, Hamiltonian is not local. It's not an element of the algebra, but we can consider just linear combination of the elements of this algebra localized on different sides. So we define just a map from this. So we call such Hamiltonian zero chains because we just have a map from the lattice to the elements of the algebra local on this side. And we consider this semi-norms on such Hamiltonians, which is just supremum of all possible sides. And this Hamiltonians define some derivations of this algebra. So the sum of such elements of J is not element of the algebra, but if you consider commutator with some element of the algebra A, then this thing is well defined and it is an element of the algebra. And they define this sort of nice, well, what we call nice derivations of this algebra, if the zero chain is self-adjoint. And we can consider truncations of this Hamiltonians to some region. And finally, we can introduce exponents of these Hamiltonians, which are like automorphisms of this algebra defined by this equation. So we have some one parameter family of such zero chains, and well, it defines some paths in the automorphism of this algebra, and we call this path locally generated automorphism. So it contains information about this Hamiltonian. And important thing why we really want to consider this, well, that is holds for this algebra is Lieb-Robinson bound, is that when we do this evolution with such Hamiltonians, we're still in the algebra. So we have some observable and act on it by this locally generated automorphism generated by the zero chains, then its application to, well, so to the element of the subalgebra is still in this subalgebra. And this Lj is form a group, so we can like define zero chains which correspond to composition of such chain, of such Ljs, and they act on states. And this will be like formalization of this equivalence of states under evolution by some Hamiltonian. And a really important thing why we actually use this kind of algebra with faster than any power decay is that is a result first discovered by Hastings, that if we have some local Hamiltonian for some system, so this like original Hamiltonian which is gapped, then we can always construct this zero chain using this integral expression, such that it gives us this evolution of the states of ground states of such Hamiltonian. And the point is that this function that appears here in the integral, it is super polynomially decaying. So we cannot make it like exponentially decaying, for example. So this is like the fastest possible decay that we can do to construct such Hamiltonians. And since we want to like, somehow work with like stably to like consider all possible dimensions simultaneously, then we don't want to have any like reference to the dimension. So some of the result might be true in lower dimensions if we like allow some decay, which is some power decay. But if we just consider super polynomial decay, we already can do many things. And it was later formulated in the infinite volume precisely by Bachman, Naptorgeli, and others, and more recently by Agathe and Moon, a stronger version of that, which we actually use. Okay, and now we can finally define what we mean, define the problem that we consider. So by product state, we mean just tensor product of pure state on-site states, so that for any observables A and B which are localized on different sites, their average is factorized, so it's a product of averages. And we say that state is in a trivial phase on some algebra defined on a lattice if it can be stacked with another product state on some other algebra, such that the resulting state is LGA equivalent to some product state. So there is some LGA that transforms it, completely disentangles it. And states which are invertible and which we are interested in are states such that we can compose them with some other state and apply some LGAs to get product state, so that the resulting state is in a trivial state. And stabilization here, so we want to do some stabilization. It's not a priori clear how to do that, but one way to do that, which seems to be natural, is to consider our system to be embedded into some high dimensional system. And instead of like considering like this LGAs which are localized on d-dimensional space, consider LGAs in this high dimensional space, but which preserve some fixed pure factorized state. So like in this picture, so we have some two-dimensional lattice, and we consider LGA alpha of f, which preserves the state. But this zero chain that generates this automorphism, it can be truncated to a half space. And its truncation produces some state which is localized, almost localized in this sense that state far away, like rapidly, like faster than any power approaches this pure factorized state. Well, so it produces some state which is actually invertible. And the reason why it is invertible is because we can consider another truncations to a lower half space. And then like the composition of two sides, well, this states will be like completely decoupled from each other, but their composition, it can be disentangled by the following expression. So it's alpha times inverse of first truncation and inverse of the second truncation. Such thing, well, composition in this group of LGA is actually localized, almost localized on the boundary between this an interface between half spaces. And it completely disentangles this the whole state, the composition of these two states. So, and the inverse map is also done similarly as this Allenberg-Swindle trick. So if we have some invertible state on a d-dimensional system, we can just create pairs of state anti-states in the upper half space and then annihilate them in a different order. So it produces some LGA. So this is just one way to stabilize all that. That seems natural. And it will be useful, as you'll see in the definition of some invariants of such phases. And of course, we can consider a G-equivariant version of all that. So we can consider some group action of and which will be just considering unit reaction, but in principle, physically relevant is also to consider anti-unit reaction, like time reversal symmetry. And we'll be assuming that this action is on site, so that each site is actually in some representation, unitary representation of this group. And the section corresponds to some automorphisms, which is just conjugation with all, well, tensor product of all these unitaries. And we can define in the same way G-invariant subalgebra, G-invariant zero chains, and G-invariant LJ, and consider equivalence of states up to this equivalence by G-invariant Hamiltonian. And note that there might be some states which are in a trivial phase, so they can be completely disentangled by some Hamiltonian, but which are in the non-trivial G-invertible phase. So it's not possible to disentangle it by G-invariant zero chain. And such states adopt SPT phases, symmetry protected states. And let me now try to describe what can be done with all these definitions. So in low dimensions, so we still have some progress only in like 0, 1, and 2 dimensions. And well, in 0 dimensions, sort of trivial, because well, we all know that all possible gap states for like finite dimensional systems, it's just CPM, right? Like space of states. But we want actually some stable version of that, and we can formulate stabilization in the following way: that we consider some half chain of spins, but spins which are far away from the origin, they should be entangled very well, slightly with degrees of decay. Well, the entanglement should decay faster than any power with a distance from the end of this half chain. And one can show that all such states, they can be produced by this element of the algebra, which are almost localized at site 0 by some unitaries which are almost local there. And it's not hard to see that space of such states is CP infinity, so it's just infinite. So effectively, we make our system infinitely dimensional by the stabilization. And well, all states are in the trivial phase, but still the space is not trivial, so it has non-trivial pi2, and it is responsible for what's called Berry class. For any quantum mechanical system, there is a natural curvature on the family of such states, and the class of this line bundle, if it is non-trivial, then it corresponds to the fact that we cannot produce all the states by some smooth family of this LGAs.
Nikita, I think you have a typo on the first line. It says all invertible 0D states, right?
Sorry, yeah, that means 0D states, right? Okay, now what is more interesting is there invertible 1D states. That's where the problem really starts. So we can, without loss of generality, assume that the lattice is just Z, because like all lattices in one-dimensional space, which are the Delaunay sets, are equivalent in the sense that is needed for us. And important fact that was proved by Hastings, that for any gap state in one dimensions, the entropy, von Neumann entropy of any interval is uniformly bounded. That is what's called area law, because it means that, well, it's like kind of law that people expect to hold for any gap state, that like entanglement of some region is grows as an area of that region, but it was only proved in one dimensions, where area is like 0, so it's just some constant. And based on this fact that this entropy is finite, the states in finite volumes, they can be well approximated by some ansatz, which is called matrix product states. And like a lot of intuition for physics come from this fact, so they made a lot of predictions based on this assumption. But it is not enough to define this the space of such states. And for that, we have to consider infinite volume. And in that case, the fact that it can be approximated by the matrix product state is not enough. However, what some important result that follows from this area law was proved by Matsui is that if this entropy is bounded, then if we consider von Neumann algebras associated with half-lines of the state, then they actually type 1 factors, which basically means that our Hilbert space, GNS Hilbert space associated with a state, we can represent it as a tensor product of some Hilbert spaces, which are associated with the left and the right half-line, and this von Neumann algebra is just algebras of bounded operators in this Hilbert spaces. Yeah, the fact that well, people actually believe that all gap states are in a trivial phase, but no rigorous proof of that exists. But it is possible to prove that all invertible states are actually in a trivial phase, and that can be done using this trick of with creation of a pair of state anti-state. But first, we should note that because of this boundness of the entanglement entropy, we in this split property, we can construct some state which coincide with, which is also pure and coincide with a given state, invertible state on the right, and which is almost factorized on the left. So that spins far away are almost disentangled from the rest of the state, and such states, they can be actually produced by some local LGA, which can be shown by this picture. So we first kind of create pair of state anti-state, and then annihilate this half lines. So first, like apply LGA that create this pairs on layers 2 and 3, and then on the next picture we annihilate this half lines on the first 2 layers, and the resulting state on the first 2 layers is some zero-dimensional, basically zero-dimensional state. So that spins of again state which is almost localized near the side, and we can produce, well, since space of such states in 0 dimension is trivial, I mean it is connected, then we can produce any other 0-dimensional state by some local LGA localized on this side. And in this way, we can move the state on the first layer. So we can consider again this fifth picture, which is related to the fourth picture, again by this creation of tails. But important point is that on this picture now the original, well, it coincides with the original state only on a half line, which is shifted by 1. And this way we can kind of disentangle completely this state on the first picture, and one also has to argue that like this one-dimensional state can be actually produced by a tensor product of such states on 2 different layers. So we can start with this final picture and then again create these pairs of states anti-states and do similar manipulations to actually get the full one-dimensional states on both half lines. Okay, so invertible phases are trivial, but the space itself is not trivial, and it is expected that it should have homotopy type of KZ3. So it should have non-trivial pi3, and this space itself was not defined yet. But what we're able to do is to construct certain class for a family of such states, of some smooth family. We can construct a certain line bundle JERP and some connection on this line bundle JERP in terms of this LGAs, which describe the space of states by some local charts, and construct certain class. So we call it higher Berry class because it's generalizes this usual Berry line bundle, but there is no canonical curvature in this, so there is always some choice. But the class itself is canonical. And I also, well, I won't be discussing fermions today much, but I'll just mention that in a fermionic case, actually there is a non-trivial phase, just Kitaev chain, and it is believed that these are only possible choices. But I guess it should be possible to prove it also using our formulas. It was now let me move to G-invertible case, so some G-equivariant case, and it was predicted long time ago that such G-invertible state should be classified by cohomology group of G, third cohomology groups with coefficient on Z, or second with coefficient on Q1, but it was first rigorously defined only recently by Ogata for finite group. I'll be talking mostly for finite group, but some results are also applicable for non-finite groups. But I'll just focus on that for simplicity. Let me remind you that the class can be just defined by some function depending on two elements, which satisfy some cocycle condition up to certain equivalence. We can produce this function in the following way. So we have this automorphism that acts on our algebra. And since it's on side, we can just consider its restriction to a half-line. Since this automorphism preserves the states, since we consider G-invertible states, G-invariant states, then the resulting state that we get after application of this automorphism on a half-line is some almost localized state. So it's just zero-dimensional states in our sense, the stable version of zero-dimensional state. And since all zero-dimensional states are invertible, we can construct some LJ which is almost local on this site, and consider just composition of the following LJ. So for two different group elements. So it doesn't matter whether this LJ preserves symmetry or not. We just want to construct some LJ. But important point is that the resulting function that we get, it defines a cohomology class, and it is actually independent of all these choices. So the properties are summarized here. So what kind of choice we make here? We make, well, on this picture, we choose some half-line, and we choose some LJ localized on the boundary of this half-line. And one can show that if one varies this line, well, considers different half-line and considers different LJ, then this function that we get, like average of this zero chain, which is local, and so average is well-defined, this function actually changes only by expression of this form, so with some function beta of G. So the class is well-defined. And moreover, the index is actually locally computable. So we can, by that I mean that we can consider like large enough region and compute some function nu by this average. And if the region is large enough, this function would be very close to the one that represents this cohomology class. And this index is multiplicative under composition. So the properties that we expect. And moreover, it is possible to, using our formulas, to prove that actually this is a complete invariant of the phase. That if any two phases which have different value of this index, they're in different phase. And it's usually harder to prove completeness, so it's much easier to just define indices. But in one-dimensional case, we already can do some completeness results. And that is example of non-trivial phase. So how to construct it? So we just consider some lattice on Z. So we have some. We can choose some homology class which corresponds to some projective representation of this finite group, and we can consider the following state. So each site is assumed to be a tensor product of these two projective representations, but of projective representation is dual, and the resulting representation is already non-projective. So it's a system that corresponds to, well, that is defined according to our definition. And the state that we consider is just what is called like entangled pair state. It's just a linear combination of, so it's just maximally mixed state between this spaces W and W star on two different sides. So like each side is entangled with each its neighbors, but total state is not is non-trivial. So and one can do this computation. So I can consider like restriction of this automorphism to half space, and after application of it, the state changes, but it changes only on one entangled pair. And of course, this change can be undone by some local unitary, and that corresponds to this LJ kappa on this picture. And I want to stress that for definition of this index, we really don't use Hilbert space at all. So we can define some GNS Hilbert space and like consider some unitaries corresponding to some this local LGAs, but we don't really need it. We just have to use this zero chain, well, this LGAs and the corresponding zero chains to define it. But the important point here was that all zero-dimensional states, they're invertible. Now let's move to two-dimensional case, which is much more interesting. And the reason why it is interesting is because it is believed that even in the absence of any symmetry, there should be some non-trivial invertible phase, but this phase was not constructed. So there is no example of that, though everyone believes that it should exist. And it is expected that the space of such states is Z times KZ4. So the most interesting piece is this Z, because it is actually related to some physical effect called thermal Hall conductivity, just like similar to electric Hall conductivity. And it corresponds to the following, that we have a system with very small temperature, so that it is much lower than the gap of this system. And we consider energy current on the edge of such system. And it turns out that this current is, well, it should be proportional to temperature square by just dimensional analysis, but the coefficient in front of it, it should be in some units quantized, and it should be related to this invariant. But how to define it without like considering this like physical picture, like just at zero temperature, is a mystery. And for fermionic systems, actually we know that such system exists, and we know that in the free fermionic case, they classified in the absence of any symmetries by invariant Z, and which is also correspond to this thermal conductivity. But we don't know again how to prove it in the interacting case. But we can say something about this KZ4 part. So it is expected that there should be some generalization of this Berry class, which in this case would be some bundle 2 job, U1 bundle 2 job over all that. And this part is related to the indices for invertible states in the presence of symmetry. And that's what I'm going to discuss next, how to define these indices. So it was conjectured long time ago that such states, they're classified by fourth cohomology group of this of finite group G. But it was defined only recently rigorously using now formalism, and it was done independently by Ogata. But ideas how to do that were presented in this paper by Nayak and else. So basically, we just had to make sense of what they were doing. Well, again, this class that corresponds to this third homology class, it can be represented by some function, a U1 valued function, which satisfies certain cocycle conditions, which is this pentagon identity, and up to some equivalence of this sort. And the crucial fact, again, to define this index is that we now know that the space of one-dimensional states is invertible. And we can use that to define certain LGA that produces the same state as a truncation of automorphism applied to a half space. So we can consider this action of symmetry G, consider its application to a half space, and the resulting state, as I described in the picture with the stabilization, it's actually invertible because we can also construct its anti-state by acting on the lower half space. And if the state that we start with is in a trivial phase without any symmetry, then well, by the same trick, like splitting their LGA into two parts, into upper and lower half plane, we can show that the resulting state is invertible. And then we can consider some combination of the same kind as in for one-dimensional index. That is that preserves the state, and that can be further split it into two halves, such that the application of this halves to some half line, it can be undone by some local LGA. So it is already defined by this longer expression. But everything is constructed from this higher dimensional block. So we just consider some natural composition of this high dimensional objects to produce something in low dimensions. And we again produce some U1 valued function that defines some class in a third homology class. And we can prove the same properties for one-dimensional index. So it is not, it doesn't use the Hilbert space. And all this data that additional data that we use to define this function, like particular choice of this half space, particular LJs which correspond, well, produce the same states. The index, well, the class of this function, it doesn't depend on all that. And it is also locally computable and multiplicative. But unfortunately, we still don't know how to prove completeness of this index. So this is this part was not done yet, but well, perhaps it can be done similar to this one-dimensional case. And let me give an example of such state, which is already constructed in this original physics paper, where this state was, where this classification was proposed. And let me first show the picture how it looks like. So it's kind of similar to one-dimensional case, but now it's a square lattice. So we have sites consisting of 4 different Hilbert spaces with the basis parameterized by the elements of the group. And different Hilbert spaces of a single site, they're entangled with the neighbors, as in this picture. So we have a certain state on a tensor product of 4 Hilbert spaces of 4 different sites, like living in the corners of this squares, and this the action of the group on this Hilbert spaces is defined by that expression. So it is constructed such that it depends on the class of H3. So we have some function, and we use it to define this group action. But with such group action, the phase is actually non-trivial. So we could somehow somehow define it in a frame where this group action is natural, but then the state that we describe would be harder to describe. And we can do the same procedure like in one-dimensional case, but with two-dimensional system, like do this restrictions and like consider LJ that the local LJ, well, LJ that computed actually, and get this function that gives this homology class, and to see that it actually is the same as this class that we have chosen to define this state. Okay, so this is a two-dimensional case. Let me just mention what happens in high dimensions. But first, let me say that everything was done only for finite groups, and we don't know how to do that in full generality. But some results can be done for a U1 group, which is most physically relevant because it corresponds to electric charge and hole conductivity. And it's possible to define it using similar methods and to show that it is actually quantized. Moreover, well, since this coefficient is related to some transport coefficients, we can like compare this coefficient for bosons and fermions. And it turns out that for bosons, it should be twice as big as for fermions. And now we can prove that. But yeah, we don't know how to do that for a general group. And to apply all that in high dimensions, we first have to understand invertible states in low dimensional case, because if you want to do like the same procedure, like restricting all this, well, the group action to the boundary, the resulting state is invertible, but we should know whether this invertible state is actually in a trivial phase or not. And that is an abstraction to we have to overcome to apply these methods in high dimensions, well, in 3 dimensions. But in high dimensions, it's actually known that this one natural guess that this cohomology classification should hold in any dimension. But we know that in dimension higher than 3, that, this classification by unitary action of group by group cohomology already breaks down. There is some counterexample, and it is believed that they're classified by a cobordism group, which comes from this Fried-Hopkins result. But yeah, it would be nice to actually get it from lattice systems. And some of the results were also done in the case of fermions. The indexes were constructed in 1 dimensions for 1-dimensional systems. But there are, of course, a lot of other things to do. Now physicists have kind of conjectures how everything, I mean, what kind of invariance we expect for lower dimensions in 2 and 3 dimensions. And it would be nice to make some mathematical theory out of all that. Okay, I guess that's all I wanted to say. Thank you.
Thank you very much. Any questions?
I have one comment on the question which was asked in the, in the chat. When you were describing the simple case, where the invariant was with H3, it reminded me exactly of the invariant which I had defined very, very long time ago in 75 for classifying the actions of a finite group. I was looking at the finite abelian group first on the hyperfinite factor of type 2-1. What I found is that there was an invariant of the action which was an element of H3 of the group with coefficients in Z, exactly similar to what you have. So that's one reason, if you want to think that, because what happened then was quite interesting in the sense that, von Jones then, so I had classified in my paper the periodic automorphisms of the hyperfinite factor of type 2-1. And then von Jones in his thesis classified the finite group actions. And then he had this absolutely remarkable idea that it was not so much the action of the group which was important, but it was the fixed points. So, so my question is more like when you are considering this system where you have a finite group action, there is probably an extremely interesting problem, which is to extend the situation to the case where you have a subsystem of finite index in your system, and there is no necessarily a group around. In fact, I mean, the theory of subfactors tells you that what you have around is the real generalization of finite group actions. And this is how Von Jones was led to his new invariant for knots. So I mean, it's an extremely rich topic. Even in the fundamental algebra, even in the factor case, it's an extremely rich topic. So what you are doing, because you go to higher dimension, would suggest that there could be, you know, an analogous situation of that in higher dimension also, which would be surely extremely interesting. You see, what I mean is that, I mean, the meaning of the discovery which I made at that time was that there was a complex number which was arising naturally as an invariant of automorphisms. And that led me eventually to find a factor which is not anti-isomorphic to itself. It's a little bit, you know, like the Kobayashi-Maskawa, the Kabibo-Kobayashi-Maskawa matrix in a breaking of a CPT, of C in physics. So here it's the same, because what you are getting invariants which are, as you say, you know, with values in U1. So you have complex numbers around, and you probably have a lack of invariance under C if you look carefully in the theory. When you pass to the complex conjugate, you probably change the invariant in some cases.
Yes,
you probably have a breaking of C. That's what I'm saying. But if you want, the great steps that Von Jones took, which was extremely courageous, was to forget about the finite group and only look at the subsystem, which is the fixed points. And to understand that there were more such subsystems than those that you would obtain by looking at finite group actions. And then, okay, this turned out to be related to quantum statistical mechanics, which is where we are, and to Eke algebras and to a number of things. So if you want, it's very tempting to try to take the same step, which is a very bold step. Huh? Yeah.
Mm-hmm.
What I find very, very interesting in what you say is that if you want, in what I was doing, there was H3, so which is H2 with coefficients in U1, of course, but I had no occurrence of the higher cohomology group. So the fact that you have higher cohomology groups means that there is something really new there, of course, in higher dimensions, yes. Which is not, if you want, reducible to I mean, I liked, for instance, when you were mentioning, of course, the term factor in the theory of fundament, of course, comes from the fact that the type 1 factorizations just factor the Hilbert space as a tensor product.
Yes. Mm-hmm.
So I mean, so what I mean is that there is something which is richer than just that when you go to higher dimensions, and it would also be very good to understand what it means algebraically from the point of view of algebraic, the algebraic formulation of quantum statistical mechanics. I mean, that also would be really relevant, I think. Because I think, in the case which is visible on the slide, well, it's probably related to this classification of automorphisms, of factors. I wouldn't be surprised. I wouldn't be surprised in that case, because you were talking about the factorization. You probably there, in that case, have a very specific factorization at n, and to relate it to that invariant would be a great step indeed.
Yeah, I don't know whether they're related, so I have no idea about that. But yes, thank you for your comment. But well, this appearance of high-dimensional classes, it's kind of well, at least I have intuition about it as more like when we consider high-dimensional objects, we consider like some high categorical objects.
I understand that very well. I mean, and it was exactly the statement that you have a kind of spectrum. I mean, you have this omega operation, which is raising the dimensions. So indeed, yes.
Yeah.
So it's like taking successive loops. I mean, yes, yeah.
Right. Yeah, and yeah, I don't know. Is there any relation to this other factors? But yeah, thank you.
Other questions? Nikita, you say that the spaces are expected to be KZ3 and then Z times KZ4 and so on.
Right.
Why do we expect this? What can you explain why the space of invertible states should resemble, for example, a KZ3 in this one-dimensional case?
So the idea is that well, it's basically just expectation from this Kitaev idea. Yeah. So because if we expect that the spaces form loop spectrum, and we know that in 0-dimension space is KZ2, then we should naturally expect that in 2 dimensions we have KZ, in 1 dimension we have KZ3, and then 2 dimensions KZ4, and so on. But this is not just this trivial spectrum. The thing is, like in 2 dimensions, we expect that there is more to that. So there is some new invariant that appears at 2 dimensions, and we don't really have an idea how it looks like in 3 dimensions. I mean, there is an idea that comes from this Fritz-Hopkins conjecture, but from the lattice point of view, we really don't understand that. Yeah, so this is just expectation from this idea of Kitaev.
Maybe more optimism than anything else.
Well, this KZ3, there is some intuition why this KZ3 appears. So, but in 2 dimensions, yeah, we don't know how to do KZ4. But what we can do is we can also do this construction of this high-Berry classes. So we can consider some maps from families of states into the space, and the fact that we can construct some invariants which are non-trivial, it's kind of already a clue that the space should have these non-trivial cycles. And we can do that explicitly in 1 dimensions, and even construct this like bundle job.
And in higher dimensions, you don't have even an expectation. Is that right? I mean, if I ask,
well, in dimensions
8,
higher than 2,
example.
in dimensions higher than 2, yeah. Well, I mean, if you don't consider this like Fritz-Hopkins conjecture, yeah, but from lattice point of view, yeah, we don't know.
I would like to just to say, yeah, there is a conjecture, right? We don't know why. There's a conjecture, may be true, maybe not true, but there is a precise conjecture about what this spectrum is.
Yeah. So there is a conjecture, but it's just it doesn't originate from some lattice models. So it's just based on assumption that everything is described by some topological field theory. But yeah, another like thing that would be good to do. Well, the thing is, like all this like G-equivariant case, it's kind of natural to consider this G-equivariant case from the point of view of like homotopy theory. So just consider maps from space, well, from BG to the space of states without any symmetry, and consider some homotopy fixed points in this space. And the fact that there are these pieces like KZN, it precisely corresponds to this cohomology classification. So this, because this maps precisely correspond to this non-trivial maps from BG to this space. And that's also a good indication why we expect that this KZN pieces should be part of this space of invertible states. But as I said, this cohomology classification breaks down in high dimension, and this is precisely because the spaces are not exactly KZN. But we don't know how to really make it like this picture precise. So it should be, I believe it should be possible to just describe this maps from BG to the space of states in this lattice framework, but we just don't know how to do that. But that will automatically give us invariants from this invariants of families for in the G-equivariant case.
Thank you. Any other questions? If not, then let's thank our speaker one more time for the inspiring talk. Thank you.